Welcome to the C-Learn Security video lesson on packetfu library. Packetfu is a Ruby library for reading and writing custom packets to and from a network interface with a high-level methodology. Packetfu allows one to use raw socket without the need to know low-level packet manipulation, formats, or encoding structures. Packetfu provides a framework to create custom packets at each level of the OSI stack, network, transport, and so on. It can also be used to sniff, filter activities, and more. The best way to learn how to use packetfu is by using the interpreter. In this video, we will mainly use pry to interact with packetfu. Let's start using packetfu. The first thing we need is to run the pry interpreter. Now that we are within the interpreter, we have to require the packetfu gem using the simple require command. As we can see, it works. Indeed, the command returns true. Let's try to list all the packetfu classes. As you can see, we have loaded the packetfu namespace and we have a lot of classes to use. Since we don't want to write the packetfu namespace every time, we can include it as a mix-in using the include method. Thanks to the previous command, we are now free to use the packetfu classes without writing the packetfu namespace before them. For example, we can directly use ICMP packet or TCP packet and so on. You can imagine it is very useful, especially if you work with the interpreter. The first class we want to use is utils. This class contains utility methods. For example, by running the command utils.ifconfig and the relative interface we want to use, we will obtain information about our machine interfaces. Here, for example, we can see the IP address, the MAC address, and so on. Utils can be used to perform an ARP request using the ARP command. Another useful method is who am I? It returns some information about the default network interface used by packetfu to write packets. This information includes the source MAC, the IP address, as well as the gateway MAC address. Now that we know how to get information from our network interfaces, let's see how to forge a custom packet. Common packet classes provided by packetfu are ARP packet, ETH packet, IP packet, TCP packet, and UDP packet. In the first example, we will use ICMP packet to perform a simple ICMP request. So let's create a simple ICMP packet typing I equal ICMP packet.new. As you can see, the interpreter prints the fields of the ICMP packet just created. We have to fill in fields like the source MAC and IP addresses, the destination IP, and the destination MAC address. Obviously, we can fill them one by one, but as we have seen previously, the utils.whoami method stores some of those parameters. So let's create another ICMP packet specifying the utils.whoami as the configuration parameter. As you can see now, we have some of the previous fields already set for us. For example, the source IP address, the source MAC address, and the destination MAC address are already set. In order to create a working packet, we have to specify the destination IP address. For example, we want to ping a Google server available at 173.194.35.55. So let's set it by typing i.ip_deadder equal 173.194.35.55. Now we have to specify the type and the code of the ICMP packet. Since we want to send an ICMP echo request, the type is 8 while the code is 0. ICMP echo requests usually have a data field that we can set by using the payload attribute of the ICMP packet instance. Now that all the required fields are set, we have to recalculate the checksum of the packet using the recalc method. We are ready to send the packet. Before sending the packet, let's open Wireshark to see what's happening on our default network interface ETH0 when we run the command. Let's edit the Wireshark filter in order to display only ICMP packets. We can do this by typing ICMP in the filter field. Now we can use the I2W method that writes our custom ICMP packets to the ETH0 interface. As you can see in Wireshark, we have the echo request packets forged using packetfu. Particularly, we can see all the fields that we have set using packetfu, such as the type, the code, and the data value. Here, for example, we can see the payload we set in packetfu. As we can see, we also have an ICMP echo reply coming from the Google server. It means that our packet has been properly routed to the destination. Let's now see another interesting example that uses TCP packets. We know that in order to establish a TCP connection, there's a three-way handshake that's required. But we also know that the handshake is performed by the operating system and we cannot control it. This means we cannot use System API to send custom TCP packets. However, we know that there are some tools that allow us to send crafted packets. For example, Nmap allows us to perform a TCP send scan that sends only the first packet of the TCP handshake. As you can imagine, this can be achieved using raw sockets, but we need a deep knowledge about them. However, we have seen that packetfu provides a framework to forge custom packets, and forge a TCP send packet is as easy as the previous ICMP example. Packetfu manages raw sockets for us, providing a high-level structure for the TCP packet creation. That said, let's see how to create a TCP send packet. The target of our test is the NetBIOS service running on the machine 192.168.3.14 on port 139. The first thing to do is to create a TCP packet using the whoami parameters. As you can see, a TCP packet has more fields if compared to an ICMP packet. This is because of the TCP header. The target machine 192.168.3.29 belongs to our internal network, so we must change the destination MAC address with the MAC address of the target host 192.168.3.29. We can recover the correct MAC address thanks to the utils.arp. Here it is. Let's use the same command in order to assign it to the TCP packet parameter eth_dadder. If we display the packet once again, we can see that now the source MAC, source IP, and destination MAC are all set. Let's now set the destination IP address. Right now we have set all the required Ethernet header and IP header fields. It's time to fill the TCP header too. The destination port is 139, so let's use the command t.tcp_dport equal 139. This can also change the source port. For example, let's use 4500. The last thing to do is to enable the TCP send flag. So let's type t.tcp_flags.send equal 1. As you can see, the interpreter shows that the TCP send is enabled. Note the S in the TCP flags parameter. The TCP packet is now ready, but before sending the packet, we have to use recalc in order to calculate the checksum of the packet. Now we can send the packet on ETH0 interface using the 2W method. Before doing this, let's open Wireshark once again to see what happens. Now that Wireshark is running and sniffing all the TCP packets, let's go back into our terminal and write the TCP packet on the ETH0 interface. As you can see, the TCP send packet has been sent by packetfu. The target service responds with the second packet of the TCP three-way handshake, the SYN-ACK packet. Finally, we can observe another packet, which in this case is unexpected. From what we can see, our machine has sent a reset packet or RST packet. This happens because packetfu uses raw sockets to send the SYN packet. Therefore, our OS kernel does not open a real socket for the connection, and when it receives the SYN ACK packets, it cannot find any socket performing the three-way handshake. In this circumstance, the TCP standard imposes that the OS can respond with an RST packet. The flow is a bit different when we send a SYN packet to a closed port. Usually, if there are not any firewalls, the target OS responds with a reset ACK packets to tell that the port is closed. It is a TCP standard. Let's verify this behavior by sending a TCP SYN to the port 200. Let's start by changing the destination port to 200. As is customary, let's run recalc and then send the packet to the ETH0 interface. As you can see, we don't have a SYN ACK because the port is closed. Rather, we have a reset ACK response, so we can identify that the port is closed this way. It is exactly what is done by Nmap. In this video, we have seen how to use packetfu in order to forge custom packets without directly managing raw sockets. As you can imagine, we can use packetfu to write our own penetration testing tools. For example, it may be useful to forge intentionally malformed network packets to test if some target services are able to handle the error correctly. This concludes the video. Thank you for joining us.